Callahan talking about my Python's a little rusty. Please welcome him.
Hi, my name is Dan Callahan. I work for Mozilla in our developer relations group. You can find me on Twitter as @Callahan. I want to talk about a lie that we tell ourselves in the Python community. And that lie is not the right button. There we go. That lie is that Python's fast enough, and if it's not, I can just write a C extension. Hands up if you've ever used that to justify using Python to a boss. Yes, like, oh no, it's plenty fast. We can just write a C extension. And this is a lie because, on the one hand, Python isn't fast enough for certain types of workloads. And on the other hand, with apologies to the entire scientific computing community, the rest of us, we never actually write C extensions. And why don't we? The main reason I think that we don't write C extensions is that other people have done it for us, right? If you look at projects like CPython, 400,000 lines of C inside CPython. NumPy, 166,000 lines of C. More than half of NumPy is C. Pillow, about 40,000 lines of code, half and half, C and Python. Have you ever used Flask? Flask depends on Jinja 2, which depends on the library called Markup Safe. 800 lines long, almost 200 lines of C in a file called speedups.c. So we're able to get away with not writing Python because so much of the Python community has already done this for us, right? And so we're kind of standing on their shoulders. But the nice thing about C is that it's incredibly portable. And it's easy to call Python to C, it's easy to call C to C. And so we're standing on the shoulders of these Python hackers who also knew C, but then they're also standing on the shoulders of other C hackers. So take Pillow. Pillow's 40,000 lines of code. It does image manipulation. It doesn't implement a JPEG decoder because libjpeg exists. The same libjpeg that's used by Firefox, by Chrome, by Pillow, by a dozen other projects that represents 90,000 lines of code or so that didn't have to get rewritten for each of these cases. Because C is portable, C is kind of like the Latin of software, right? You write it in C, you can bind it from almost anywhere. The other reason we don't write C is because writing C is really, really scary. And that's primarily because memory management in C is hard. Like, C will take off all the safety belts and let you do whatever you want. And it kind of looks fun. And you kind of get to do things that you probably shouldn't do. But the last thing it is safe. Well, we'll play that again. Oh no, maybe we won't. No. The web. So let's talk about memory management. Memory management is hard, and we see that with bugs like Heartbleed, Ghost, CVE 2015-0080, which didn't get the memo about having good names. That was a bug that was fixed in Internet Explorer's PNG decoding, where if you sent IE a specially crafted incomplete PNG, instead of erroring or instead of displaying part of the PNG, it would say, oh, there's some bits missing here. I'll just go grab them from other random parts of memory. And so in that image would be parts of maybe some cookies, maybe some saved passwords. Basically, if you loaded enough of these, you could dump the browser's memory space, which is not a good thing for an image decoder to do. And I look at that, and I work for Mozilla. I don't mean to pick on the IE team because they're doing great work. But I look at that and I say, my lord, I am not smarter than the glibc or the OpenSSL or the IE developers. Like, I'm just not. If I go and try to write C, I would be lucky if that was the worst that happened to me. So I don't do it, right? But what if you had to write C? What if, most batteries are included. Our community is awesome at developing packages, so there aren't a lot of wheels that haven't been invented for us. But what if you actually do need to write some C because you want to make the next matplotlib or you want to make the next NumPy? It would be really great if you could write C without writing C, right? Like if you could write something that gave you C's performance, C's portability, C's embeddability, but guaranteed that you were doing it safely. And that guarantee is what we're trying to achieve with Rust. Rust is a programming language that Mozilla has been developing for the past 5-6 years. And it's designed to be a replacement for C in systems level programming. And when I say systems level programming, I mean the sort of programming where you start to have to care about how the computer works, how memory is managed. You have to understand the difference between the stack and the heap, which is something that higher level languages like Python hide from us and give us a lot more efficiency at development time because we don't have to think about these details. But in Rust, you do. As a quick refresher, the stack is managed by the CPU. Kind of whenever you enter a function, your locals get stored on the stack, and when you leave that function, they get popped back off. And so it's really fast, it's really small, it's automatically managed, and it stores function locals. The problem with this is that it's compact. So any sort of memory or data structure that could grow in memory, like a list, can't live on the stack. You have to have a pointer to somewhere else, because if that was on the stack and then you appended an item to it, it could clobber something adjacent to it. So we have this other region of memory called the heap, where you can say, give me a chunk of memory this big. And it holds globals really well, it lets things grow, but it's not managed. And that's what we're going to talk about today. This idea of like managed versus unmanaged languages, and something that's really unique that Rust is trying to do to bridge this gap. So when I talk about managed or unmanaged memory, or managed or unmanaged languages, people are talking about memory management. So I didn't have time to make nice HTML5 slides, so we're gonna go with the whiteboard. This is Rust syntax. I'm declaring a variable x. I'm saying x equals box new 5. Box new is just the Rust syntax to say allocate this memory on the heap and give me enough memory for an integer and put the integer 5 there. And then we're going to try print line x. You'll notice this is kind of Python 3 style format strings where you have the curly braces. So good job, Python. When we run this, we hit that first line. And yeah. Web technology, right? Like slides, it's all perfect. So we have that 5 on the heap, and then we come down here and we print out 5. The question is, what happens when we get to the end of this block? What happens to that 5? In a language like C, you're expected to manually manage all of your memory. You're expected to allocate that memory yourself, and when you're done with it, you're expected to explicitly free that memory. But that's really hard to get right, because you have to remember to do all this bookkeeping. You might free something when it's not actually done being used, whatever. In languages like Python or JavaScript, you have a garbage collector that at some point your program will stop running. The garbage collector will come in, look at all the things pointing into the heap, and clear everything else that's not reachable. And that's super convenient because it means that you can't make certain mistakes, but it also means that your program doesn't necessarily perform consistently, because it'll have these pauses, and you'll get this jank where like, oh wait, the thing stopped, it's doing a GC, all right, now it's running again. Rust tries to strike a middle ground where you don't manage your memory manually, but it also doesn't have a garbage collector. And so what Rust does is it analyzes this code and introduces the notion of ownership. When the compiler looks at this code, it says, all right, this line is going to allocate memory, and I'm going to assign it to x. And so this chunk of memory on the heap, I'm going to give responsibility to it. It's going to be owned by x. And so when x goes out of scope, the Rust compiler will insert a call to free that memory. This works a lot like a context manager in Python, where you can say, with open file as f, and when you come out of that block, you know that that file is going to get closed. You can think of this similar to that, but for memory allocations. Super useful, right? Because you get good performance. But what if you try to trick it? So let's declare a variable y outside of this block. We allocate x on the heap. We hit there. We now have an alias to that point in memory. We print out 5. And now, when we hit the end of this block, x goes out of scope. And because the lifetime of that memory is bound to the life of x, when x goes out of scope, that memory gets freed, and y is pointing to garbage. And it turns out that we can look at this and figure out that that should be a problem. So can the Rust compiler. So if I try to actually compile this, I'll get an error that says, wait a second, x does not live long enough. So the Rust compiler won't even let me run this code because it knows that it's not going to be safe. Pretty nice. It's a safety belt. It doesn't let you jump out of your truck and go down the slide. And this actually, this notion of ownership lets us do some really interesting things. The other, oh wait, hang on, there we go. Reveal.js is awesome. But what if we did want to, so we're here, we've got a compiler. What if we did want to build something in that block and have it outlast the block? What if we wanted to like do some object setup and then pass it back out? What we're doing on that second line is we're creating a reference to x with the ampersand. If we take that out, instead of creating a reference, we're passing ownership. So when we hit that second line, the ownership table gets updated and it says, all right, actually this memory is now owned by y. And when y goes out of scope is when it's going to get freed. The trick here is that when we get to this line and we try to print x, we still have a pointer, the memory is still valid, but this is actually a compile time error as well. Because the Rust ownership model works similar to ownership in the real world. If I have a book and I give you my book, if I transfer ownership of my book to you, I can't read that book anymore without borrowing it back from you. And so when this ownership changes, it invalidates any previous reference that came through the old owner. Just like if I gave you a book, again, I would have to borrow it back from you. I just don't own that thing anymore. I can't use it. But if we take that line out, if we stop trying to use x after we've given it away, then this will compile and print out 5. And now we've kind of built something in this box, hoisted it up into a longer lifetime. In a nutshell, these ownership rules, which enable a lot of really important checks at the compiler, boil down to you get one owner, one unique owner per memory allocation. And that memory is freed when that owner leaves scope. To avoid dangling pointers and things like that, any other pointer to that same memory location also has to go out of scope at the same time or before the owner goes out of scope. That's enforced by the compiler. You can hand off ownership, and that invalidates the prior owner's reference. And then lastly, just syntactically, we use an ampersand to denote references, and in the Rust community, we tend to call that borrowing. The best part about this is that all of these rules are enforced statically at compile time. So if your Rust compiles, you're guaranteed that you don't have dangling pointers. You're not going to use after free. There's no pointer arithmetic to get wrong. There's no null pointer dereferencing. And all of this comes at 0 runtime cost. All of this is done statically by the compiler at compile time. So it checks that your code is safe and compiles it, and it doesn't have to insert these checks while your code is running. Rust is big on zero-cost abstractions. If you read more about the language, there are a lot of other really cool things we do in that same vein. Let's talk about mutability, which is another area where Rust tends to do things a little bit differently. So I've got a really basic program that, spoiler. I declare x to be 1, I try to increment x, and I try to print it. If I try to compile this, I get an error that I'm reassigning an immutable variable x. So every variable in Rust by default is immutable. You see this in languages like Clojure, et cetera. This lets us reason at the compiler level, lets us reason a lot more about how memory is going to be used, how things are accessed, and it's key to a lot of the safety that Rust brings to the table. So if I want to be able to mutate this, I need to annotate it as let mute x equals 1. Compile that, run it, and we see 2 as our result. Everyone follow? I see nodding heads. Excellent. Let's make this a little more complicated. I've got 2 functions. Add1 takes a mutable reference to a 32-bit integer. It dereferences it, increments it by 1. So this is kind of like an in-place update, an in-place increment. And then our main function, we're going to have a mutable value x. We're going to mutably borrow x and give that to add1. And then we're going to print it out. So this should, if it works, give us 6. I was able to save it. There were no errors, so let's try running it. Behind the scenes, I'm using a Vim plugin for ease of demoing. Behind the scenes, this is using rustc and just compiling the file. We get 6. It works. But this goes kind of crazy if we change one little thing. If instead of saying and mute x here, if we try to assign that outside and say let y equals unmute x, and then pass y in, this should work, because it should be functionally identical to this, right? We just moved that, we hoisted this inline variable into its own thing. But I get a compile time error down here that I cannot borrow x as immutable because it is also borrowed as mutable. This comes into lifetimes again. One of the things that Rust enforces is this idea that there can only ever be one unique reference to something that is mutable. And this helps us prevent data races. So it kind of acts as a syntax, a compiler level semaphore that lets us lock out any sort of data race. Like if you want to read data from this and something else has the ability to mutate it, compiler is going to fail. So the way we solve this is we have to have y go out of scope before we try to use x. Because having this mutable reference alive is what's blocking us from reading x. So we know how to do that. We can just put that inside a block, so it'll come out of scope here, y goes away, this should work. It compiles, it runs, and we're good. And this isn't just, a legalistic language for the sake of hurting your head and making you spend a lot more time debugging. What this gives you is some really interesting principles that you can actually reason about multi-threaded code. You can actually have parallelism and in a way that is hard to do safely in any other language. And we're not just talking. We're building a browser engine called Servo, which is an experiment that's been co-developed with Rust. This is Servo rendering GitHub. It can render a lot of the web right now. And we've kind of developed Rust, developed Servo, and the two have informed each other, so we know that Rust is actually good for writing this sort of software system. And it lets us do things in parallel. This may look like a broken rendering of Reddit. What this is actually doing, each different color of box indicates the CPU that was used to lay out that part of the page. So Rust is doing just extremely parallel browser layout. This is unique right now. There's been some theoretical, academic CS that's had to move forward in order for this to happen. In the real world, we see performance, because we can utilize cores more efficiently, for about 40% better or so than Gecko on a lot of websites, which powers Firefox right now, which means we can also run your CPU at a lower rate and get similar performance, so you get better battery life, et cetera. Servo is not going to be released. We're using it to learn about how to build these things, and we hope to take what we learn and build it into Firefox in the future. But this is a Python conference, and I swore to you that I would tell you how to use Rust from your Python code, and I have not done that at all. So, I've got a really simple Rust program here that has two functions. This function double takes a 32-bit integer x, returns a 32-bit integer, and it's just going to take x and double it. To make this function available to see, all I have to do is annotate it with don't mingle the name, and make it a public external function. And then down here I have a test. If the test works, double 3 should return 6. So I can test this by using cargo, which is our build tool. I can say cargo test. Running test, it works, okay. Okay, so that function works, it doubles the number that's given. And we're going to try calling that from Python. So I'm using a library or a module called cffi, which is like ctypes, but way better. And the way you do that is you import ffi, you initialize it, you say cffi.cdef, and you paste in a C-style library header. So if you were writing C, you just copy and paste your .h file. Rust doesn't have those, so you have to kind of write it yourself. We want to be able to generate them in the future, but for now you have to hand write this part. I come down here, I say ffi.dlopen, I pass it a path to my library. You can install this on your whatever path so it can be discovered. And then down here, all I have to do is say c.double, which is the function name from Rust, and I can pass it an integer. And so if I run this, I get 6. Python to Rust and back, really easy. But, thank you. That was a really lame demo. Let's do something fun. Oh, sorry, does it need to be more up or more over? More right? All right, well here, let's just do this. Warp. That's the wrong right. There we go. Projectors. All right. So let's go into here, and let's look at this program in Rust. This is a program that exposes a function to C called triple, takes an integer, returns an integer. What I'm going to do in here is I'm going to, from 0 to 10, kind of like Python's range, so I'm going to get 10 things, I'm going to map over them, and I'm going to start a thread for each one. And that thread is going to report that it's running. It's going to start a counter at 0, count to 10 million, finish, and then once all of these threads are done running, it's going to report x times 3. And this lets us report like a triple value of a number really quickly because we warm up the CPU a lot. Pro tip. And here's equivalent code in Python. A little more comprehensible, but the same basic deal. Here's our target. We're going to count to 10 million. We're going to return. Once all this is done, we're going to return the triple. And then if we run this, it's just going to do triple 3, right? So let's start up Activity Monitor and get a CPU graph up here. We'll put that over here. And so if I run gil.py, see all my threads start. I'll make this window, oops. Oh, sorry, move that a little up. Do this again. All the threads start. It takes about 8 seconds. I have no idea what this artifact is. Takes about 8 seconds, and we get 9 out. So Python, using threads, kind of slow. Let's see how fast the Rust does it. Cargo test. OK, hang on. How fast is that? Time. OK, about 0.2 seconds to do the same exact computation in Rust. And this isn't because Rust is more efficient or faster, necessarily. It's because Python has the global interpreter lock, which prevents more than one thread from making progress at a time. And so not only are we cutting our possible like CPU-bound throughput to a fraction of what it actually is, there's also a lot of overhead in locking and unlocking those threads to make sure that the GIL is held and only one thread moves at a time. So let's make this a little more challenging. Let's edit the Rust and say, let's count up to 1 billion. And now when I run it, you can see all of my CPU is getting saturated. And it should finish in about, also, because these are running in parallel, you can see the printf is super mangled, and we're done, about 10 seconds, right? So let's see what we can do from Python. So again, I'm saying, here's my definition. Returns an int, it's called triple, takes an int. We're going to run it, right? I run that. I really wish I knew what this artifact was. But anyways, what you can see is my Python actually saturating all 4 cores. This is something you cannot actually do from Python because of the GIL. But with Rust, you can sidestep that and actually have legit parallelism. Yeah, a couple of claps. No, I don't have a lot of time, so I'm not going to go too far into this. But if you look at this function, I've got a Rust function that takes a string. It goes over every character in the string, starts with an accumulator at 0, and says, all right, if I see a plus, increment, minus decrement, star, double, slash, half. And so if we have a program like this, we go 1, 2, 4, 3. Half is 1.5, but it's an integer. It's truncating arithmetic, so we should get 1. Cargo test. Test passes. We can call this from Python by saying, all right, we've got this function calculate that's going to take a character pointer. Here we go, so it should be 1, 2, 4, 5, 10, 9, and then half, 4.5. So we should get 4 out, truncating division, right? This is passing a string, a byte string, to a Rust function from Python. If we run calc.py, it works. So you can pass more complex data types than just integers and other primitives. And the way you do that is super gross, and I'm not going to talk about it. All this code's on GitHub. You can ask me questions later. I want to have an open space to discuss this tomorrow. But for now, I want to point you to resources to learn more. Rustlang.org is fantastic. Has a really great blog. There's actually something about fearless concurrency with Rust on the top of Hacker News right now, which talks about these same sort of benefits. The static compile time checking, the borrow checker, the limited mutability, gives you a lot of really cool benefits. You can read more there. There's also a really friendly IRC channel and subreddit, which is kind of shocking, but kind of fantastic, worth checking out. If there is time, I'd like to go to questions. You can find the slides on github.com/Callahan/PyCon2015-Rust, and I think the mic will be in the center of the aisle there. Thank you.
We have time for a couple questions.
So the whole idea is like the next time you get to somewhere where you're like, I really should write C for this, try writing it in Rust and see if you get something equivalently fast but safer.
So it's really cool that Rust has automatic garbage collection when you exit out of scope. For security conscious code, is there any way to automatically null out the area of the memory before it actually frees the memory?
To automatically do what?
Free the memory. So don't just release the memory, but null everything and then release the memory. Is there any hooks like that in Rust?
I'm not aware. You could probably, and you could definitely do something. Rust has the ability to denote blocks as unsafe, which let you go and meddle with things just like with C. And the nice thing about that is like inside an unsafe block, like if your Rust program crashes, you know that that seg fault came from somewhere in one of those unsafe blocks. So inside that, you could do whatever you want.
So there's a lot of C libraries out there that manage their own memory in various ways. They have objects and a set of objects with bound lifetimes to each other and reference counting. Python is obviously one of those C programs with its own rules for memory management. Could you talk a little bit about how you bridge foreign memory ownership concepts to Rust?
Frankly, I can't because I'm a Python hacker and I don't have much experience at that level. But Rust itself can trivially interop with C as well. So at those boundaries where you're going from Rust to another language, all bets are off, and the compiler kind of accepts that.
Yeah. What's the CPU architecture support like in the code generator at the moment for Rust?
So we use LLVM as our backend. So basically things that LLVM target, Rust should work on. I know that we work on x86, x64, ARM. I think there's a port of Servo to Android that is currently maybe working. So we have pretty broad architecture support. There are people actually doing this in production. Yehuda Katz has a startup called Skylight that it's a Rails monitoring gem. So you like gem install Skylight and it'll watch your Rails process and report on errors, memory usage, things like that. And that needs something that's really efficient and it needs something that won't crash the app so you can leave it on in production. And so they've actually shipped a gem, a Ruby gem, that has a heart made out of Rust and have like paying people using it. We could do the same in the Python community.
Yeah, this will be the last question.
Oh, apparently that was the last question.
Can you hear me? Okay.
Yeah, there we go.
Instead of creating a brand new language, do you think it would have been possible to implement all of the checks the compiler currently does as a C preprocessor, say?
I asked some of the core team that had been around from the beginning of that, and they assured me that they tried that as their first path and just were not able to get to that point with a C preprocessor. So, cool. Thank you all so much. Again, you can find me on Twitter. I'll tweet links to the resources, and I'll see you at PyCon.